Laplace transformation. Whereas if you want to transfer an S domain signal into the time domain signal, the corresponding transformation process that is known as the inverse Laplace transform. Mathematically, Laplace transform of f of t, that is going to be f of s. So small f of t become capital F of s, and Laplace inverse of f of s, that is going to be f of t. So capital F of s become small f of t. This particular step is called the Laplace transformation, and this step is called the inverse Laplace transform. Now, how to do the Laplace transformation? Suppose we have a signal f of t, which is a time domain signal, and if you are interested to transfer the signal into time frequency domain, the given signal we have to integrate from 0 to infinity multiplied by a constant term called e raised to minus st times dt. So this particular step will give you the S domain signal or the S domain output. So any signal, if you are interested to transfer into any time domain signal, if you are interested to transfer into Laplace domain or the S domain, simply integrate between 0 to infinity multiplied by e to the power minus st dt. So let us consider first case. So first example, suppose f of t is k, where k is a constant, and we try to find out the Laplace transform of f of s. So as per the basic equation, we are going to integrate between 0 to infinity given function, which is k to the power, multiplied by e to the power minus st dt. So k is a constant, take it out, then you have to integrate e raised to minus st. So this e raised to minus st integration will give you e to the power minus st divided by coefficient of t, which is minus s, within the limit 0 to infinity. So what is most important to remember? E raised to minus infinity is 0, e raised to infinity is infinity, and e raised to 0 is 1. So please remember this particular relation. So if you apply the upper limit, or if you take this minus s out, then we have the upper limit, which is e raised to minus infinity, lower limit is e raised to 0. So this is going to be minus k by s, e raised to minus infinity as per this equation it is going to be 0, e raised to 0 which is 1, then this minus and this minus makes it plus, so we have the answer is k by s. So this meaning is that f of t, if it is a constant k, then corresponding f of s is k by s. So if f of t is 1, f of s is going to be 1 by s. If it is 10, it is 10 by s, and so on. So let us consider another example. If f of t is equal to t, and we will try to calculate the Laplace transform of f of t. So again, as we said before, f of s is calculated by the equation 0 to infinity, given function is t multiplied by e raised to minus st dt. So here we must apply the product rule, assuming that this is the first function and this is the second function. As per the integration rule, first function into integration of the second with the limit 0 to infinity minus integration of derivative of the first, which is dt by dt, into integration of second. This whole thing is supposed to be in dt with the limit 0 to infinity. So if we do that, we'll get t into e raised to minus st. If you integrate, we'll get e raised to minus st by minus s within the limit 0 to infinity minus, this is going to be 1. So 0 to infinity, if you integrate this term, we'll have e raised to minus st by minus s times dt. If you do further integration, if you apply the upper limit, it is going to be infinity, but e raised to minus st is going to be 0. So the whole term will be 0. Then if you apply lower limit, it is also 0. So the answer is supposed to be 0 minus 0. And if you take this minus s out, we'll have 1 by s integration 0 to infinity e raised to minus st dt. Then this can be written as further 1 by s into, if you integrate this term again, e raised to minus st divided by minus s within the limit 0 to infinity. That will give you 1 by s. We apply the upper limit, e raised to minus infinity minus e raised to 0. This will give you what? 1 by s. Sorry, there is divided by s square. So I am going to take this s square out. It will be minus 1 by s square. Minus 1 by s square. This time is 0. This is going to be 1. So the answer is 1 by s square. So what you have seen in this case, that Laplace transform of t will get 1 by s square. Now, as a general rule, f of t, if it is t raised to n, then the f of s is obtained by the equation n factorial divided by s raised to n plus 1. So let us try now. Suppose if f of t is t power 1, that will give you corresponding f of s will be 1 factorial divided by s raised to 1 plus 1. That will give you 1 divided by s square. If f of t is t square, we will get f of s is equal to 2 factorial divided by s to the power 2 plus 1. That will give you 2 factorial is 2 divided by s cube. Same manner, if it is t raised to 5, then f of s is given by 5 factorial divided by 5 plus 1. 5 factorial is nothing but 1 time, 2 times, 3 times 5, 4 times 5 divided by s raised to 6. Now let us try to look at a exponentiation function, which is e raised to minus at, and what will be f of s. So we'll apply the same rule. F of s is obtained by the equation 0 to infinity e raised to minus at into e raised to minus st dt. As we said before, the given function multiplied by e raised to minus st, integrate from 0 to infinity. So if you do that, 0 to infinity, I'm going to take this t minus t out, then we'll have s plus a dt. Now, if you integrate, we'll get e raised to minus s plus a divided by minus of s plus a within the limit 0 to infinity. If we apply the upper limit, it is going to be minus infinity. So if you take minus 1 by s plus a as a common factor, which is out, then after that we apply the upper limit, it is going to be e raised to minus 0 minus e raised to 0. So e raised to minus infinity minus e raised to 0. This will make 1 by s plus a times 0 minus 1. If you simplify, this is going to be 1 by s plus a. So Laplace transform of e raised to minus at, we got 1 by s plus a. If that is the case, Laplace transform of e raised to at will be 1 by s minus a. So when there is a minus signal, minus polarity here or the minus, you will have s plus a, and when we have plus here, then it is 1 by s minus a. So now let us see the Fourier transform of cos omega t. From the trigonometry that we have already studied, cos omega t can be written as e to the power j omega t plus e to the power minus j omega t all divided by 2. So now we'll try to find out f of s as we have seen before, 0 to infinity e to the power e to the power j omega t plus e to the power minus j omega t divided by 2 supposed to multiply it by e raised to minus st dt. So here half is a common term, we take it out. Then we have e raised to j omega t. If we expand the bracket, we'll have e to the power minus j omega t plus e to the power, e raised to j omega t into e raised to minus st, e raised to minus j omega t into e raised to minus st, the whole thing within dt. So half is again common. If we're just going to consider the power by adding the powers, we'll get, I'm taking minus t out. This is going to be s minus j omega minus st plus j omega t plus, if I'm going to take minus t here, it's going to be s plus j omega dt. Then I'm going to differentiate, we are going to integrate the whole term by term. So first term is going to be half is a common factor, e to the power minus t s minus j omega whole divided by minus of s minus j omega, because the coefficient of t is s minus j omega, plus if I am going to integrate this term, the same term will exist, because integration of e raised to x is e raised to x. That is going to be divided by coefficient of t, in this case it's going to be s plus j omega with a minus sign. Okay, then the limit is from 0 to infinity. So now if you are going to apply the limit, before that we'll just take, of the bracket, we'll find minus 1 by 2 s minus j omega, first term. Then we are going to apply the upper limit. When you apply the upper limit here, the whole thing is going to be raised to minus infinity. Then the lower limit is going to be 0. So this is going to be the first part. Next part will be, there is a minus sign, 1 by 2 is common. So minus 1 by 2 s plus j omega. If you apply the upper limit, it is going to be e raised to minus infinity and e raised to 0. E raised to 0. So if you simplify this, we'll have minus 1 by 2 s minus j omega. It's going to be 0 minus 1 minus 1 by 2 s plus j omega. Here is going to be 0 minus 1. So if you simplify this equation further, there is a minus sign, so this minus minus cancel. We'll have 1 divided by 2 into s minus j omega, and again this minus minus get cancel, plus we have 1 by 2 into s plus j omega. So if you take this LCM, 2 into s minus j omega into s plus j omega, then this term will be what? S plus j omega will come here and s minus j omega will be here. And if you expand it, plus. So we have s plus j omega plus s minus j omega divided by 2 into s square plus sj omega minus sj omega plus j square omega square. J and j is something similar to I. So j times j is going to be minus 1, minus of minus make it plus. So j square is something but I square. So our this is a complex complex operator I, or j which is exactly same, so that is equal to minus 1. So if we do that, we'll get s square plus omega square, and top these two get cancelled. So we have 2s divided by 2 into s square plus omega square. This is cancelled, so we'll have our equation s square plus omega square. So in short, Laplace transform of cos omega t is s divided by s square plus omega square. So what is Laplace transform of cos t based on this equation? So 2 stands for omega. So you have answer is supposed to be s divided by s square plus 2 square, which is nothing but s divided by s square plus 4. Laplace transform of cos 100t is given by s square plus 100 square. Next we'll see the Laplace transform of sin omega t. Again, from trigonometric principle, sin omega t is given by the relation e raised to j omega t or I omega t minus e raised to minus j omega t over 2j. So if we substitute this in the Laplace transformation equation, we'll get 0 to infinity e raised to minus j omega t. 1 by 2j, we are going to take it as a common factor, 1 by 2i or 1 by 2j. We are going to multiply first term by this, minus we are going to multiply the second term by this. Exactly the same way we have done for cos omega t. So 1 by 2j is a common factor. We are going to integrate this. If we are taking e to the power minus t as common term, we will have here s plus j omega. Minus, if you take minus t out, here we'll have, this is supposed to be minus, s minus t, s minus j omega, and this is going to be minus t, s plus j omega dt. So 1 by 2j. If you integrate this term, we'll get e raised to minus t, s minus j omega divided by minus of s minus j omega minus e raised to minus t, s plus j omega whole divided by minus of s plus j omega within limit 0 to infinity. So as we done before, we are consider part by part. So the first term I'm going to consider 2j. This term I'm going to take it minus s minus j omega. Then if you apply the upper limit, it is going to be e raised to minus infinity minus e raised to 0. First part is done. Minus 1 by 2j is here. We are taking this term out. So it's going to be plus s plus j omega. Then we will have e to the power minus infinity minus e raised to 0. Then if you simplify this is further, minus 1 by 2j, s minus j omega. Here we have 0 minus 1 plus 1 by 2j, s plus j omega. This term is going to be 0 minus 1. So then this minus and this minus makes it plus. So I have 1 by 2j s minus j omega. This is already plus. So that plus and minus makes minus 1 divided by 2j into s plus j omega. As we had done before, we are considering 2j into s plus j omega into s minus j omega as a common factor. Then this side will have s plus j omega minus s minus j omega. So if you expand the bracket, we have s plus j omega minus s plus j omega divided by 2j into s square. If you expand it, s square plus s j omega minus s omega will be cancelled. j times j is going to be minus 1 omega square. So that is make it s square plus omega square. In this case, these two things cancel. So we have the numerator 2j omega divided by 2j into s square plus omega square. So 2j cancel. The answer is omega divided by s square plus omega square. So we can say that Laplace transform of sine omega t is omega divided by s square plus omega square. So let us apply some practical case. For example, we have sine phi t. Laplace transform of sine phi t is what? Phi divided by s square plus 5 square, which is 5 divided by s square plus 25. For example, sine 100 t, that will make you 100 divided by s square plus 100 square. Now we will be looking at some of the composite functions, where a given function f of t, if it multiplied by a term e raised to minus at, what will be the corresponding output? So Laplace transform e raised to minus at f of t is going to be f of s plus a. So let us try to do this case. F of s is calculated by the equation 0 to infinity. F of t is the given function. Given function is e raised to minus at into f of t. As per the basic rule, we have to multiply it by e raised to minus st dt. Now I just interchange the terms. So first term I am going to keep f of t e raised to minus at into e raised to minus st dt. So now 0 to infinity f of t. If I am going to take this minus t out, we will have s plus a times dt. So this is what we got it. This is supposed to be Laplace transform of e raised to minus at f of t. Let us compare this equation with the standard Laplace transform equation. F of s is equal to 0 to infinity f of t into e raised to minus st dt. If we compare these two equations, f of s is equal to f of t into e raised to minus st dt, and this term is f of t into e raised to minus t into s plus a. So the only difference between these two is that when it is e raised to minus st, we got the answer is f of s. So in this case we have s plus a. So which means this is corresponding to f of s plus a. So Laplace transform of e raised to minus at f of t is equal to be f of s plus a. Similarly, Laplace transform of e raised to at f of t will be f of s minus a. So what is the Laplace transform of e raised to phi t into cos phi t? What is f of s? So we know that Laplace transform of cos 10t is s divided by s square plus 10 square, which is nothing but s divided by s square plus 100. Therefore, Laplace transform of e raised to phi t cos 10t, as per our relation, Laplace transform of e raised to at f of t is equal to f of s minus a. So which means that if you are going to multiply this function by this, then in the result, wherever s is there, s has to be replaced by s minus a here. So s minus in this case s minus a, but in this case it is supposed to be s minus 5. So since it is multiplied by e raised to 5t, our s become s minus 5 divided by s minus 5 whole square plus 100. Similarly, e raised to minus 2t cos 3t, this can be written as s plus 2 divided by s plus 2 the whole square plus 3 square. Here is 2 because we are multiplying by e raised to minus 2t. Here is minus 5 because we are multiplying by e raised to 5t. So next let us try to find the Laplace transform of derivative of a function. So let's say f of t is our function. The d by dt of f of t is also called f dash of t, and the result is s into f of s minus f of 0. So let's try to do, how can we derive this particular relation. So d by dt of f of t, we can also call it d by dt of f of t is equal to f dash of t, and if you are interested to find out f dash of t, that is equal to 0 to infinity f dash of t e raised to minus st dt. Now we can do the integration by parts by keeping this is the first function and this is the second function. If you do that, we will get first function, which is e raised to minus st, into integration of f dash of t. If you integrate f dash of t, we will get f of t within the limit 0 to infinity minus integration derivative of first, which means e raised to minus st. We are differentiating this, so we will get minus s multiplied by integration of f dash of t with respect to dt. So if you apply the upper limit here, this is going to be e raised to minus 0, e raised to minus infinity, which is 0. This is going to be e raised to 0, so this part is going to be 0, and this is going to be f of 0. So if you apply upper limit, we will get e raised to minus infinity f of infinity minus lower limit is e raised to minus 0 or e raised 0 into f of 0. That is minus, if you take this term out, we have s, then we want to integrate this term. So this is 0 to infinity e raised to minus st. If you integrate this, we will get f of t dt. So if you look at this term, e raised to minus infinity, this is going to be 0 and this is going to be minus f0. Then we have plus s into, I just rewrite this equation, which is f of t e raised to minus st dt within limit 0 to infinity. Already we have seen from the basic definition of Laplace transform, a function multiplied by a function f of t multiplied by e raised to minus st dt. If you integrate between 0 to infinity, we will get f of s. So this will give you s into f of s. Then we have a term minus f of 0. So in short, you can say Laplace transform of derivative of a function is s into f of s minus f of 0. I think there is a mistake here, sorry. S into f of s minus f of 0. So if I rewrite it, Laplace transform of f dash of t, that is equal to s into f of 0 minus, s into f of s minus f of 0. S into f of s minus f of 0. So another important theorem is called the initial value theorem. According to initial value theorem, the initial value of a function is given by limit s into f of s tends to infinity. So this particular proof is derived from the Laplace transform of derivative of function. So already we said that Laplace transform of f dash of t is equal to s into f of s minus f of 0. So if you expand this, as per the last Laplace transform definition, we have 0 to infinity f dash of t into